Okay, so I'm talking about quantum money, and the outline is first I'm going to say some things about the background of quantum cryptography and quantum money, and then I'll tell you what doesn't work. And once you know what doesn't work, it'll explain some of the reasons we did what does work, which would be completely unmotivated if I just told you what does work without telling you why we did it. And to explain why we did it, I need to tell you what doesn't work. So here it goes. So I'll start back in, I guess, 1930s or so with traditional cryptography. And if you have traditional cryptography, you have two people. And here they have electromechanical computational device called an Enigma machine, but nowadays they would have a computer that runs an algorithm which takes the input and encodes it into an output, and then they send it. And the sender and the receiver have the same secret key, which means that the sender sets the rotors in this Enigma machine to a certain thing and then types in the message. And the receiver sets the rotors to the same thing and types in the ciphertext, and the message comes back out. And so one of the big problems of classical cryptography was managing the secret keys, because if your adversary intercepted your secret key, then they could listen to all your messages. And so you need to deliver secret keys to everyone who you want to talk to, and that's a lot of trouble. So the possibility of doing with cryptography without secret keys, which is called public key cryptography, was raised by Ralph Merkle in 1974. And the first really convincing way of doing it was done by Diffie and Hellman a year or so later. And Diffie and Hellman let two people who want to talk to each other have a little protocol where Alice sends Bob a message and Bob sends Alice a message, and then they do some computation and they get a key, and someone who's listening can only figure out this key if they can do discrete logarithms. And nobody knows how to do discrete logarithms without a quantum computer in any reasonable time. So that's, the first public key crypto system was for key exchange. Now, I guess people probably know a little bit more about quantum cryptography. So two of the first quantum cryptographic protocols were Wiesner's protocol for quantum money and the BB84 protocol for key exchange, which came out of Bennett thinking about Wiesner's quantum money and talking to Gilles Grassard, who together they worked out BB84. And both of these depend on the quantum no-cloning theorem. So, of course, the traditional problem with money is that someone who has a bill can make a copy of it. And if you have physical bills, you can do all sorts of things to make it difficult to make copies. But if you have electronic bills, what is an electronic bill? It's digital information. It's impossible to produce digital information that cannot be copied. So if you have an electronic bill, you can copy it. People have been trying to make copy-proof devices for DVDs and stuff for a long time, and nobody has succeeded. So you cannot prevent copying of classical electronic data. You can, here it seems, prevent copying of quantum data. Of course, you might think the quantum no-cloning theorem immediately tells you that you can use quantum states for money. But as we see, it's going to be a little more complicated than that. So the no-cloning theorem says there's no quantum transformation that takes psi 0 to psi psi for an unknown quantum state psi. And the reason is that this transformation isn't unitary. And so the history of quantum money, so Stephen Wiesner came up with this in 1970, which if you look back, the no cloning theorem was 1982, so he really anticipated the no cloning theorem by 12 years. So the idea is that each build is a sequence of quantum states in one of two complementary bases, so we'll call them polarizations, so either vertical, horizontal, or right diagonal, left diagonal. And by the quantum no cloning theorem, anyone who does not know the polarization of these states cannot copy them. Okay, so now you have a quantum bill. You go to the merchant and you say, here's my quantum bill. And he says, how do I know you didn't, forge it? And you can tell him, well, I didn't touch all these polarizations, but he can't measure them because if he does, he'll destroy the bill. So how do you check the money? Well, for Wiesner's money, the only way to check it is to send it back to the mint and have the mint check it, which is really inconvenient for money. And another possibility is the mint could tell the merchant the quantization axis and the eigenvalue of some of the qubits, and he could check those. But if a bunch of merchants got together, they could collect enough information to forge a bill they could pass. So that doesn't work either. So what we'd really like to do is we'd like to make a verification procedure that lets you have a quantum state which you cannot clone, but which you can verify. Now, let me go on with a little bit of explanation about cryptography. So, for many years, cryptography was done with ad hoc cryptosystems, kind of like the Enigma, and many of these were eventually broken. So, mathematicians started working very hard on figuring out, how to design cryptosystems that were not broken. And then public key cryptography has become even more mathematical. And of course, a lot of this mathematics is done by agencies that don't tell anyone what they're doing. But, apparently the English MI5, I think, came up with public key cryptosystems several years before Merkle, Diffie, and Hellman did. So there are two kinds of proofs of security in cryptography: security through information and security through complexity. So something is informationally secure if, no matter how powerful computer an adversary has, you will not be able to break the crypto system. And the nice thing about BB84 key exchange protocol is that, assuming you believe in the laws of physics, it's informationally secure. And a one-time pad is also informationally secure if the key is as long as the message. Once you use a one-time pad twice, it stops being secure. And computationally secure have a Diffie-Hellman key exchange and RSA cryptosystem and lots more classical cryptosystems. And these rely on the difficulty of solving some computationally hard problem. And if you're lucky, you base your cryptosystem on a computationally hard problem which really is hard, and maybe even one which, like factoring, a lot of mathematicians have thought about and have not been able to solve, so it's been tested by a lot of smart people trying to break it. So the disadvantages are that there's lots of stuff you cannot do with informationally secure cryptosystems, and it's impossible to prove anything, at least so far, about the security of computationally secure cryptosystems. I mean, you can prove that Diffie-Hellman is as hard as solving a problem which looks a lot like discrete logarithms. That's around as far as you can go. So quantum cryptography, the BB84 protocol, is a quantum cryptosystem which can solve a task with informational security, which cannot be solved classically with informational security. So the only classical way of doing cryptography with informational security is to have a key which is as long as the message, whereas BB84 does it where the two parties can communicate, assuming they have a quantum channel between them with no agreed key and you need some securities to guard against the man-in-the-middle attack, but I expect There's going to be some more talks on quantum cryptography, so I won't go into any details. So one of the things was that I was wondering whether there were any tasks for quantum computers that a quantum computer might be able to do with computational security, but were impossible for a digital computer to perform. And this is, quantum money was an idea of such a task, and I think we now have proposed a crypto system for quantum money. We have no idea whether anyone will be able to break it, but I think it looks pretty hard to break. So the task is unforgeable states, to be a little more concrete than, say, quantum money. So we would like to make quantum states that can be verified and cannot be duplicated. And what can you do with this? Oh, well. So in more detail, one of the players in the protocol, let's call her the mint, should be able to make a state psi sub I and a verification protocol p sub I. And here I is going to be the serial number on the bill. And we want psi sub I to pass the test p sub I. And we want the test p sub I not to destroy the bill psi sub I. And we finally want a possible counterfeiter holding the state psi sub I and knowing the protocol p sub I could not produce a state of two quantum systems, possibly entangled, that both pass the test p sub I. And you can see that this can only be computationally secure because given the test p sub I with exponential computational time, you can figure out the state psi sub I which would pass it. So you just build a huge matrix and diagonalize it. So that does not work informationally, but it might work computationally. So, in fact, in our protocol, we get an extra bonus that is, I think, not even the mint can efficiently make another copy of the state, psi sub I, that passes the test p sub I. So these states are really one-of-a-kind, unique objects. If you make one, nobody can make another, and if you lose it, it's gone forever. So the uses for unforgeable states, well, quantum money is one of them. The mint makes the quantum states and gets pairs psi sub I, p sub I. And now the mint has to publish a list of valid pairs I and p sub I somewhere secure so that a forger cannot add an extra pair to this list. And if you want, you can also do this with a classical, classical signature scheme. And then it hands out psi sub I together with I to a customer who wants quantum money. And now anyone who knows the verification protocol and who has a quantum computer can check that psi sub I is really the valid bill. Okay. And you could also use them for quantum ID cards because, well, they might be stolen, but they can't be forged because if you cannot copy it without destroying it. So for both money and quantum ID cards, you need to have long-lived quantum states, which don't exist yet. So far, this is completely a theoretical procedure. It might be possible to use these unforgeable states as a subroutine in some other quantum cryptographic protocol. But still, we don't have quantum computers, so that still is a theoretical procedure. Okay, so one thing, you have to be careful. So for one of the potential protocols we looked at, a potential counterfeiter holding just psi sub I could not make a copy of it because of the no-cloning theorem. If you know just the verification procedure p sub I, it appeared very difficult to make a copy of it because if you just had the verification procedure, this was an instance of a problem of random KSAT, and it looks like, and random KSAT is believed to be, or rather random quantum KSAT is believed to be a hard problem, and it looked like you could make this money so that this random quantum KSAT was in one of the hard, hard regions of KSAT. But it turned out that both holding psi sub I and knowing p sub I, you could produce 2 copies of psi sub I. And I think this thing, let's skip this. I think the way we broke this is one of the most interesting things that came out of it. So I'll just tell you a little bit about it. So in breaking the tool, we came up with possible new quantum algorithmic tool for quantum computing. And it's called quantum state restoration. And what it is given a Hamiltonian H and a ground state psi of H. So of course, H here is the verification procedure, and psi is the quantum state. So you just check that psi is the ground state of H, and if it is, then the money passes. So given the verification procedure and the ground state, one can do tomography on a small number of qubits of psi and measure local properties of it without destroying it. So if you had an unknown quantum state without this Hamiltonian, you couldn't do tomography. If you just had the Hamiltonian, you cannot. There's no efficient procedure known for finding ground states of it. It's an NP hard problem. But with a Hamiltonian and the ground state, you can do tomography on, say, three quantum bits of on any 3 quantum bits of H and find out what state they're in. So this says, for one thing, it says that any quantum money is going to have the property that 3-state measuring, doing tomography on 3 qubits of it doesn't tell you anything about the state in general. And, what I'd really like to know is whether there's some other interesting uses for quantum state restoration besides breaking quantum money. Okay, so that was a side issue. How does our quantum money protocol work? So first, we'll give a failed protocol based on graph isomorphism. Then we'll give our best current candidate for quantum money. And we do that by replacing graphs and graph isomorphism with knot diagrams and making a global replacement of other things. And then I'll discuss the general template because you have 2 instances of this template. You can imagine a general template where you plug in a different problem. So what's graph isomorphism? We already saw talk of graph isomorphism. 2 graphs are isomorphic if you can label the vertices of one, or if you can label the vertices of each of these so that if I is connected to J here, then I is connected to J here. And just looking at the 2 graphs, it's not at all clear that they're isomorphic, but if you want to, you can label these vertices 1 through 10 and these 1 through 10 and check that they're isomorphic. So it's easy to check that 2 graphs are isomorphic, but it seems hard to come up with the isomorphism. So what do we know about graph isomorphism? Well, we know that quantum computing can solve it. What we do know is if we could take a graph G and create the superposition over all labelings of G, then we could solve graph isomorphism. How? Well, take 2 graphs G1 and G2. We want to know if they're isomorphic. So we prepare the superposition over all states, all labelings of G1 and the superposition for all labelings of G2. And then we test whether this state is a +1 eigenstate of the operator that swaps these 2 these 2 registers. And if the graphs are isomorphic, then it is. And if the graphs are not isomorphic, the overlap with the +1 eigenbasis of the swap operator is at most 1/2. So you can prepare a number of these states, and if they're all +1 eigenvalues, then you have a reasonable confidence that these graphs are isomorphic. Okay, the moral from the previous slide is creating equal superpositions of a graph seems to be hard. Of course, that's if you believe that graph isomorphism is hard. If you can solve graph isomorphism, you can do this. And it turns out that for lattice, if you can create the equal superpositions of points near vectors in the lattice, so superposition over all vectors within all points within some distance of a lattice vector, then you can find short vectors in the lattice. And this is also a problem believed to be hard classically. So here's our graph isomorphism algorithm. Well, you start with the equal superposition of all graphs. So that's easy to create because you either, you put each edge into a superposition of being in this graph or not being in this graph. And that gives you the equal superposition over all graphs. And now the MIT measures some property of graphs which is invariant under permutations of the vertices. So one possible property you can measure is a spectrum. Now suppose the spectrum is S. Then we're in the state 1 over root n sub s, superposition over all G with the same spectrum of G. So how do we test the state? Well, first, the easy part is that we check that the spectrum of G is indeed S. Here, S is the spectrum, is the serial number, and this is the quantum field. And then you check that the state is invariant under the relabelings of two of the vertices. And any test state that passes these tests must be a superposition over, with some weights on it, over equal superpositions of labelings of graphs. It's, it's easy to check that actually anything that passes state 2 is a superposition of these things which we believe are hard to create if you can't solve isomorphism. So the good news is we now have this money state, and one possible way we can imagine of getting, forging it is measuring this quantum money state to get a graph with spectrum of G equals S. And now we have this graph, we create this superposition over all labelings of that graph. But we can't do this unless we can solve graph isomorphism. So you might think this is hard. The bad news is that we can solve graph isomorphism for random graphs. Graph isomorphism isn't that hard. And now you can do that by, if you can solve graph isomorphism for a random graph, if you have a graph you can solve graph isomorphism for, then you can construct this state. And how do you do that? Well, you create the superposition over all permutations, you apply the permutation to the graph, and then you uncompute the permutation. And uncomputing the permutation is exactly the same as solving graph isomorphism for this graph G. In other words, the problem of given two isomorphic copies of G, find the isomorphism. So graph isomorphism doesn't work. So our idea was, now let's look for a problem which is a little bit like graph isomorphism, but is different enough that this crypto system actually works. And we looked through a whole bunch of candidates, and a lot of them didn't work, and we think we have one that works. So we're going to propose using knots and knot invariants. And so what's a knot? This is a knot, actually. This is a knot diagram in the plane, which is an image of a three-dimensional knot. So a knot is just a closed loop, a closed piece of string embedded in 3 dimensions. A knot diagram is a projection of the knot on the plane, and anytime you have an crossing of two edges, you have to say which one goes over and which one goes under. And if you have a knot, 3-dimensional knot, there's lots of things you can do with it. You can, tangle it up and everything. And there are many, many different planar diagrams that represent the same knot. And I should say nobody knows how to test whether two knots are given by the same diagram. I got this backwards, testing whether two diagrams represent the same knot. So how do you tell whether Well, we need something that corresponds to the random, applying a random permutation in the graph problem. And this is going to be taking place of Reidemeister moves. And the nice theorem is if you have two knot diagrams that do give the same knot, you can move from one to the other using a sequence of these Reidemeister moves, where you can see that if you apply a Reidemeister move, you stay with the same knot because, you haven't, if you think of these in 3 dimensions, none of them involve moving one strand of the rope through another strand. So now we need something that corresponds to the spectrum. So we need a function f that maps knot diagrams into values that depend only on the knot and not upon the knot diagram. And this is analogous to the spectrum of G for graph isomorphism. And so, so what we, luckily, topologists have spent the last 40 years studying knot invariants very intensively. So there's many, many knot invariants around. We need one that's computable in polynomial time because we want an efficient algorithm for non-money. And the Alexander polynomial is the best known of these, but there are lots and lots of others. So we'll just pick the Alexander polynomial. And it maps a knot into a polynomial with integer coefficients. And for the trefoil knot, it turns out to be t squared minus t plus 1. And basically, the idea of a proposal is just like the idea for graph isomorphism. You start with a superposition of all diagrams of knots. You measure the Alexander polynomial of these knots, and you get the superposition over all diagrams for the same Alexander polynomial. The verifier checks that the superposition has the right Alexander polynomial, and that this superposition is invariant under Reidemeister moves, and if the state passes these 2 tests, he accepts it as valid quantum money. And now I'll only have a few more slides. There are a lot of diagrams of the same knot, in fact, infinite number if you allow arbitrarily many crossings. So you can't use this equal superposition. So what we're going to do, the idea is basically take knot diagrams between n1 and n2 crossings and weight them with some probability piece of, or some amplitude piece of k that depend only on the number of crossings. And now you have to generalize the quantum money template with the verification procedure to work on this. And you can do that by considering reversible Markov chains, and it's fairly straightforward to figure out what to do. Another problem is we've replaced knot graphs with knot diagrams is that we need to create the uniform superposition over all knot diagrams with a given number of crossings. And there might be algorithms for this. In fact, I'd be surprised if there weren't, but there aren't any simple algorithms for this. But we can fix this by using grid diagrams of knots. Reidemeister moves get replaced by grid moves, and instead of weighting by the number of crossings, we weight by the size of the grid. So what is a grid diagram? Well, you take a k by k grid, you pick 2 permutations, are a set of points, blue points, 1 in each row and 1 in each column, and a set of purple points, which have the same property, and you connect things in the same row and things in the same column, and when there's a crossing, the vertical line goes over the horizontal line. You can represent all knots this way. It's easy, given this, to create to compute the Alexander polynomial. And it's also easy to create the uniform superposition over all things like this. It's just creating the uniform superposition over all pairs of non-intersecting permutations. Okay, so how can you break this protocol? The obvious way is to find some way of mapping the numbers from 1 to n into the superposition over all into G sub I, where G sub I is the ith grid diagram associated with some knot. And for this, you really need an efficient one-to-one reversible mapping from I to grid diagrams of a given size associated with not K. And mathematicians have no idea how to do this. They don't know an efficient algorithm to tell whether two grid diagrams are associated with the same knot that always works. They can do this in practice reasonably fast using knot invariants or small knots. But this is a much harder task, and we don't know how to do that. So that's our proposed quantum money. Now, I'm going to skip ahead to open problems. So can we prove that our template, where we replace knots with some abstract set of objects and black box transformations, and Reidemeister moves with black box transformations, is indeed secure, without assuming that graph isomorphism is hard. We have some evidence that breaking knots in general is as hard as doing graph isomorphism, because we saw that if we could break our quantum money scheme for hard graphs, we could solve graph isomorphism. And we can show that if you have a way of breaking the quantum money scheme that works for everything, it'll work even on the hard graphs. So, can we use the same template to produce other protocols for quantum money? Well, Michael Friedman has a protocol based on not invariance, but invariance of three manifolds, which is standard general. I mean, it's a straightforward generalization of our proposal into one higher dimension. Are there other ways to produce quantum money? Okay, so Scott Aronson has a proposal to create quantum money from polynomials that are invariant. I shouldn't say invariant. Polynomials that are zero on certain subspaces of Z2, the binary, n-dimensional binary vector space. And that nobody has broken either. So that's another interesting one. And thank you.
So you said that you looked at many possibilities and you ended up with knots. Can you tell us, so that we don't waste time, which ones you looked at that didn't work out in the end?
Okay. Well, we looked at a lot of things that were like graph isomorphism, but there are lots of isomorphism problems, and some of them are harder than graph isomorphism, and we looked at some of these, and it didn't seem to work either. And we looked at I'm trying to remember. There was this question about square roots of polynomials over rings, and that didn't work. We haven't looked at isogenies of elliptic curves, so that's a possible thing that might work. And I think that's around it. Yeah.
So, but really, what is the evidence that we have that these knot problems are going to be average case hard, given that with graph isomorphism this is kind of the problem?
Yeah, so, graph isomorphism is nice that the decision problem is easy to turn into a function problem. In other words, if you have a procedure that if you just tells whether two graphs are equal, you can use it as a subroutine and design an algorithm that actually gives you the permutation that maps one to the other. If you have knots, suppose you could tell that two knots were equal. There doesn't seem to be any way to turn this into an algorithm that finds a short sequence of Reidemeister moves between these two knots. And to break the money, you really need to find a short sequence of Reidemeister moves between the two knots. So even though there are lots of invariants which probably will tell you whether two knots are equal. They don't give you a sequence of randomized moves. Right, but it still may be easy on average, even if it's not an NP, because there's lots of different knot invariants, and in practice, given two knots, topologists can can check a whole bunch of knot invariants and either say, well, these look like they're equal, or these are definitely not equal. But turning that into an algorithm which gets a sequence of Reidemeister moves between the two knots is the, I don't know how to do that.
Can you say a few more details about the verification procedure for the knot money?
Okay. So, let's see. I eliminated the slide to, okay, so the verification procedure is, so we have this superposition of, we have this thing which is supposedly a superposition of different grid diagrams for the same knot. Now there are a bunch of grid moves, which, let's see, where's our grid diagram? Here it is. So a grid move, you can take this column and move it to the last column, and that preserves the knot. You can interchange two adjacent rows if one of these edges is inside the other, and that also preserves the knot. And you can also create a little loop here and make the grid one size bigger. And these, with three grid moves, you can reach all grid diagrams. Now, so the test is pick some of these grid moves at random and apply them and see if the superposition doesn't change. And you have to do something, you have to weight the move that increases the size of the grid properly, because we have a weighting on, we have different amplitudes depending on the size of the grid and the superposition. But if you have the equal superposition, applying one of these moves doesn't change it. If you don't have an equal superposition, and you can show that these moves give a rapidly mixing Markov chain on the grid diagrams, then you can show that there's a unique quantum state, which is the quantum money, and anything that passes the verification test has to be close to this quantum money state. That's, yeah. And, okay.
At the beginning of your talk, you mentioned you were going to show how this quantum money could be produced by the Mint, but once they'd made one instance with a certain serial number, they could not make another instance. Right. I missed where that was then discussed.
Okay. So the idea is that what the Mint does is it measures it takes the superposition over all knots and it measures the Alexander polynomial. And the Alexander polynomial is a long and complicated thing, and there are exponentially many Alexander polynomials for grid diagrams in size n. So if the Mint wants to make another thing, well, if they want to do it this way, they create this superposition of all knots and then measure the Alexander polynomial, and they get a random Alexander polynomial. And if you throw out the Alexander polynomials, which, like, you have to throw out 0 because it's easy to get knots which give the Alexander polynomial of 0. But if you throw out any small Alexander polynomials, we think that it's exponentially difficult to, you have to measure exponentially differently many times to come up with a knot that has the same Alexander polynomial as one you've already produced. So if this is the recipe the Mint uses for making the money, then they can't make another state which is the same. And otherwise, they don't have any advantage of forging the money over anybody else.